So hello everyone and welcome for this 5th week of the course of networks. And today we're going to be talking about dynamics, linear dynamics more specifically, the important concept of timescales and the impact of symmetries on dynamical systems on networks. And this will always be done in relation with the concept of communities. So just a reminder on what we've been doing last week. So last week we've been interested in the problem of community detection. And community detection is a problem where you try to cluster the nodes of a graph. You try to find groups of nodes that are densely connected with each other. Now, these methods that we've been presenting are purely structural, in the sense that they only use the structure in order to infer groups of nodes that are of interest. And that was the case of modularity, for instance, where we've been characterizing the goodness of a partition by simply counting edges, and this is a purely structural factor, in order to say if communities were of good or of bad quality. Now, there are quite a few situations where the structure alone is not sufficient in order to understand how a system functions. And you could think, for instance, of the brain. The brain is made of a physical background, and here it means that you would have different regions of the brain that are physically connected with each other, but obviously the structure is not sufficient in order to understand important questions like cognition. And for that, you would need to understand how the dynamics of activations of the different parts of the brain are affected by this underlying topology. Another important example would be cities, and cities can also be represented by networks, for instance, by street networks. But obviously, the street network itself doesn't allow you to understand how cities function and live on a day-to-day basis. And to do so, you need to understand how all of its individuals are taking possession of this underlying network in order to move and to interact with each other. Now, these two examples motivate the design of methods that would be uncovering communities in networks, not purely from a structural point of view, but from a dynamical point of view, trying to understand if it's possible to find groups of nodes that are dense, but more from a dynamical point of view and not only from a structural point of view. Now, here in the following, we'll be interested in some linear processes, but let me first just clarify the notations that we'll be using. So we'll be looking at some graphs that are characterized by their adjacency matrix, and this adjacency matrix is going to be assumed to be, well, it's going to be a weighted one, so it means that you can have weights on the edges, but we're going to be having an undirected network, meaning in this case that the matrix is going to be symmetric. And for the rest of this course today, we'll be looking only at undirected networks, hence symmetric matrices. Now, so it means here that A is going to be equal to A transpose. Now, in the case of weighted networks, a natural generalization of the concept of degree is the weighted degree. And the weighted degree is a sum over the j's of Aij, which we note by Di. And actually, well, it's sometimes convenient to adopt matrix notations. And if you want to adopt matrix notations, we're going to be defining a vector of ones, which is n times 1 vector of ones. And from there, we'll basically have that the vector of degrees is going to be obtained from the agency matrix. Sorry, it doesn't need this here, an agency matrix times this vector of 1. Okay, so again, for matrix notations, we're going to be using the following. So we're going to be defining the diag of a certain vector x, whichever it is, as a matrix that we're going to be saying big X, such that xii is equal to xi and 0 otherwise. So it means that we'll have a diagonal matrix where we'll be putting the entries of the vector on the diagonal. So it means that from this vector D that we had, we're going to be defining a matrix big D, which is equal to the diag of D. And this is a matrix where we'll have only zeros, and then D1, D2, and so on until Dn. Okay? Now, given this matrix, well, we can then rewrite a matrix that we've seen before, that is the combinatorial Laplacian. And this combinatorial Laplacian can be seen as simply this degree matrix minus the adjacency matrix. And it's a reminder on what we've seen, that matrix is positive, semi-definite. So we have that all of its eigenvalues are ordered from 0 to lambda n. And here I've been assuming that the graph is connected, because when the graph is connected, we just have one eigenvalue that has a value 0, and all of the other ones will be positive. Okay. Now, this matrix, this Laplacian, naturally appears in many dynamical systems, and in particular, it appears for models for consensus dynamics. So consensus dynamics is a class of models. There are many models for consensus dynamics, some based on the Laplacians, others that might be nonlinear ones. And these are models that are used, for instance, if you want to model the formation of opinions in societies of individuals, or if you want to design some algorithms that would be decentralized in order to calculate in a distributed way some global functions, for instance, when you have sensors that are interacting with each other. So what is this simple model of consensus dynamics that is based on the Laplacian? So what we'll do is we're going to be considering a graph. And then what we'll do is we endow each node I with a state xi that belongs to the real number. Now, the time evolution, so this is the states, and now what we're going to be assuming is that the nodes are interacting with each other, but only with their neighbors. That's going to be leading to a time evolution of this state. And this time evolution is going to be given by the following matrix equation. So we'll have minus L times the vector x. And here, well, we have the Laplacian, and this is this consensus dynamics. Now, if you want to understand where this equation comes from, it's kind of practical. It's important to rewrite it in terms of their entries. And so I have that xj is going to be equal to a sum over the j's of aij times, sorry, I'll do it like this. I think it's going to be more convenient like this, j times xj minus delta ij times xi or xj, which we can rewrite as a sum for all of the j's of aij times xj minus xi. So it means that what does the equation do? It means that for node I, its evolution is going to be governed by the states of its neighbors. What you do is you compare the state of I to the state of its neighbors, and you look only at the difference, and you basically try to minimize the difference and to reach the state of your neighbors. Now, this is a very simple dynamics, and this is a fairly intuitive one, right? Where you try always to reach a consensus with the states of your neighbors. Now, obviously, this set of differential equations needs to be complemented with a certain initial condition, x0, which is the vector x, when time is equal to 0. So we have some initial conditions. Now, when the graph is connected, it can be shown that this system of equation reaches global consensus. And this global consensus, actually, you can know what would be the values. You will have that the xi's, all of them, will converge to x star when t goes to infinity. And this x star, this consensus state, is simply obtained from an average of the initial nodes in the graph, of the initial states of the nodes in the graph. So it's going to be obtained by the vector of 1's transpose times x0 divided by n, which is simply equal to a sum over the i's of x0 index I divided by n. So you just do an average, an arithmetic average of all of your initial states, and that will give you the final state that is reached by all of the nodes. And that's why you see that, for instance, if you want to calculate an average across measurements that are made by many sensors, and you want to do this average in a decentralized way, this algorithm gives you directly the answer. Now, this is good for decentralized calculations, but is it good as a model for opinion formation? Because this model shows you that through interactions, all of the agents reach global consensus. Well, we know from elections, American elections, for instance, that clearly, even if the people are interacting, it doesn't mean that they reach consensus. And even sometimes they can even become more and more separated and segregated. And that's one of the reasons why this linear model is usually used as a first order model, and that actually more complicated ones are then used in order to model more realistic consensus dynamics. Cool. Okay, so here in the following we'll be actually looking at consensus dynamics that takes place on networks. And what we're going to be interested in is not the asymptotic state, because the asymptotic state is somehow trivial, we know it. We'll be interested in the intermediate states, in the intermediate regime, and in this approach towards consensus. So here, as an example, let's look at the Karate Club. Well, in the Karate Club is a graph that we've seen before. We know that there are two communities, right, that are basically driven by these two nodes that were competing with each other. And here, what I've been doing is the following. In this plot here, I've been giving random initial conditions between 0 and 1 to all of the nodes. I colored some of them blue, those from the blue community, some in red from the red community, and then I let the dynamics evolve. You see that asymptotically, indeed, all of the nodes reach the same state. This is perfectly fine. But what you see as well is that there is an intermediate regime where actually you can see a separation between the opinions of the blue and the red nodes. And you actually see some sort of local consensus inside the blue community. Some approximate local consensus inside the red communities, and then these two local consensus converge together towards the global consensus. And this is here clearly the sign that the presence of these communities is affecting the asymptotic approach of the dynamics towards the asymptotic state. Now, another situation where the communities would be affecting the dynamics that I just mentioned here, because we will not do it in detail, would be the situations where you would be putting some inputs on the nodes. And for instance, you could be using a positive input on this node here and a negative input on this node there, and then you let the same consensus dynamic takes place. And if you do so, what you observe is again a separation, and in this case an asymptotic separation between the states of the nodes, with the blue ones that reach a positive value typically, and the red ones that lead to a negative value. And hence again you have that the states of your dynamical systems are completely aligned with the communities that you know are present inside your graph. Now, this is what's happening for consensus dynamics. But actually, there are other linear dynamics that can be defined on networks. And one such linear dynamics would be the one of random walks. And so random walks can be argued to be somehow like the dual process of consensus dynamics, and this will be clarified in the next weeks. But this is a model that is usually used in order to model diffusion of information or items or quantities on networks. And it's akin to the heat equation that you know from continuous dynamics. to be something where you'd have an initial probability that's going to be diffusing, like for the heat equation. In the case of networks, we basically have that the time evolution is given by this equation. So we have the P transpose at time t plus 1 is equal to P transpose at time t times a certain transition matrix. And this transition matrix is equal to D minus 1A. Now, where does this equation come from? So again, let's write it for Pi at time t plus 1. It's going to be equal to, let's call it Pj, a sum over the i's of Pi at time t times Aij divided by Ki. So here, if you want to know what is the probability to be on a certain node j at time t, you need to consider its neighbors. And for each neighbor I, you will look at the probability that was present at the previous time step. And you will say, okay, this probability is going to be distributed between the neighbors of node I. And so, for instance, if node I has a degree 3, I will have here 1/3 of it, because of the 1 over Ki, 1/3 of that probability that is going to be going there, 1/3 going there, 1/3 going there. Yep. And you have to sum, obviously, over all of the neighbors of node j. Now, this process is linear again, and this process can be interpreted as a Markov chain. So it means that many of its properties can be derived from standard properties of Markov chains. One thing that is of interest is that if the graph is undirected, as we consider, if it is connected, and if it is not bipartite, non-bipartite, and if you remember, a bipartite graph is a graph where you can divide your graph in two sets, and all of the connections are between the sets. So you don't want to have a bipartite graph. But if these relatively light conditions are satisfied, you can show that all of the PIs are going to be converging to a certain equilibrium distribution that we write P star, which is equal simply to the vector of degrees divided by 2m. So it means that asymptotically, you will not reach a uniform situation like in the case of consensus dynamics, where we reach some consensus. Here instead, asymptotically, the distribution will be not uniform, and you will have that at equilibrium, the probability to find a worker on a node is proportional to the degree of that node. Now, you can play the same game as we did before on the Karate Club, but this time with random walks. And so here, what I'm showing are situations where I start with all of the workers either on this node, and that would be here, or on that node, and that would be there. And if I do that, you can see that for long times, indeed, we reach a certain P star that is the same independently on the initial conditions. And that is indeed something that is not uniform with the node 34, for instance, that is this one that has a high degree, has a higher probability of having random walkers, while, for instance, node number 17, that would be here, has a small degree and has a small probability of having random walkers at stationarity. Yeah. So this is consistent with this ergodicity of the process. But if you look at the intermediate regime, then you can see something very different. If we started from the red, we actually have that the probability at intermediate times looks like the stationary one inside the red community, but is almost empty for the blue community. So it's as if we had reached some local equilibrium inside the red community, but we didn't have the time to explore yet the rest of the graph and to reach the blue community. If we started from blue, that's the opposite. We reach something that looks like the stationary state inside the blue community, but didn't have the time yet to reach and to explore the red one. And in each of these two cases, what basically happens is that we are yeah, we are reaching some local equilibrium, and this local equilibrium is actually, yeah, constrained. It's going to be due to the existence of these communities inside the graph. Now, what we'll be doing in the next video is to look at the math behind the emergence of this local equilibrium, and we'll first do that on very simple models before trying to understand really what is the relation between the structure, that would be the presence of communities, and, as we'll see, the importance of different timescales that are associated to the existence of, to the emergence of this local equilibria for the dynamics. So hello, so in this video we'll continue on the previous one, and we'll be interested in the notion of timescale separation for dynamical systems, and especially when the dynamics is basically constrained by an underlying network, trying to understand what is the relation between the structure and the dynamics, and how does the structure induce some possible timescale separation for dynamics. So what do I mean by timescale separation? So let's assume that we have a dynamical system where that we're going to be writing like this, where we're going to be having a certain separation of the times at which different parts of the system evolve. And so here is an example. We'll have a system just with two variables, where we have the x and the y that are coupled with each other. But actually, because of the presence of this epsilon here, we clearly have, and so the epsilon is a number that is much smaller than 1, we'll actually have that x of t changes much more rapidly than y of t. And this is obviously due to the fact that the dy by dt is epsilon times something, so it's going to be something that is very slow. So we have here the x that is a fast variable, and we have that the y is a slow variable. Now, this interpretation in terms of different times at which things evolve can be rewritten just by defining a new time variable tau that is equal to epsilon t, which is going to be a slow time variable. And if we do so, we can rewrite the system as dx by dt is equal to f of x, y, and dy by dt is equal to, dy by d tau, excuse me, is going to be equal to g of x, y. And so here, when the epsilon is sufficiently small, we'll be assuming that there's going to be a separation of timescales in the dynamics. And what we'll see is that when you have such a separation of timescale, well, if you're interested in the dynamics for the small times, or if you're interested in the dynamics for the long times, actually you're going to be able to exploit this timescale separation in order to simplify your dynamical process. So let's assume, for instance, that you are interested in the short term. Well, at the short term, for small values of time, y has not had the time to evolve yet. At least as an approximation, because epsilon is very small at the time to evolve. Which basically means that the whole dynamics is going to be driven by dx by dt is going to be equal to f of x, y0. Y is simply going to be a constant, and we'll basically have that the whole time evolution at the fast time scale for short times is going to be that dx by dt is a one-dimensional system. So we started from a set of two equations that are reduced to one equation if we're interested in the short-term dynamics and we have this timescale separation. So this allows you to coarse-grain your dynamics and to simplify it, to reduce the number of equations that are necessary to represent your system. Now, similarly, if you're interested at the long term, now let's assume that the system dx by dt is equal to f of xy. When we fix the y, converges to a certain x star that depends on y. Yeah? So if we fix the y to a certain value and we let the system evolve by dx by dt is f of xy, let's assume that this system has just one basically asymptotic state independently on the initial conditions. Well, if that's the case, basically it means that when we're interested in the way the system evolves at the slow time scale, well, we can assume that the x for any value of y has always reached its stationary state, and that actually the whole system can be rewritten as dy by d tau is going to be equal to g of x star of y, which means again that now if you're interested in the long-term regime, well, you'll be again simplifying your set of two equations into one single equation, where this time we'll simply make the assumption that the x has reached its asymptotic state, and then once it has reached its asymptotic state, the y evolution starts to evolve. And again, it means that you've been reaching one equation. So in one case, you are using the value of y initially. In the other case, you're using the value of x asymptotically. But in both cases, you started from two equations and you arrive at one single equation. Now, what about timescale separation for consensus dynamics? Well, for consensus dynamics, if you look at your differential equation, and that was that x dot was equal to minus L times x, well, you can write it formally as x is going to be equal to exponential of minus LT times x0. Yeah. Now, this is a formal solution, but it doesn't tell us much about how the dynamics look like. And if you want to gain more understanding and intuition, it's very practical to use a spectral decomposition of the Laplacian L. And the Laplacian L is symmetric because we've been assuming that the adjacency matrix is symmetric and the graph is undirected. Now, what we do is we look for the eigenvectors of L. So we look for these eigenvectors that are such that this, because because the matrix is symmetric, well, first of all, we will be ordering as usual the eigenvalues. Yeah. And because the eigenvectors are the eigenvectors of a symmetric matrix, we can use them as a basis for the space. And we're going to be rewriting the L as by using the spectral decomposition, the sum over the alphas of lambda alpha v alpha transpose, from which we see that the x of t is going to be equal to a sum over all of the alphas of exponential of minus lambda alpha t times v alpha transpose times x0. Now this here is just the initial condition. It's just the projection of the initial state x0 on the direction associated to the eigenvector v alpha. Yeah. Now the rest here tells us how in this direction v alpha the modes are going to be evolving in time. And clearly for lambda 0, for lambda 1 we have 0, so we have a constant mode, and this is actually the stationary state. This is the consensus. But for all of the other values, we're going to be having exponential decays. And these exponential decays are going to be happening with a time scale t alpha equal to 1 over lambda alpha. So the larger the eigenvalue, the fastest is the relaxation of that mode. So what would be the implication of this kind of consensus dynamics? Well, let's assume that we have eigenvalues that are such that we have small ones to a certain beta, yeah, and these ones are much smaller than the rest of them. Well, if that's the case, it basically means that if you look at your expression here with your combination, your sum of exponentials, and you look at it for a certain tau 0 of the order of 1 over lambda p plus 1. Well, at that time scale, you will have that all of the modes here are going to be vanishingly small. And actually, the whole dynamics will actually be represented with a very good accuracy only with the dominant, well, with the space that is spanned by the dominant eigenvectors. So it basically means that if you have such a timescale separation, well, you're going to be able to simplify your sum that was using here n terms, and many of those terms will be neglected because at a certain time, some of the terms will be much, much, much smaller than others. And so it means that you will go from n to beta equations, well, no, n-dimensional system to a beta-dimensional system in the case where you have such a timescale separation. Okay? Now, this is something here where we've not been using much about the graph. What we've just been saying here is the fact that if we have a separation in the eigenvalues of the Laplacian of a graph, it will lead to a timescale separation, and it will allow us to simplify the dynamics and to reduce the dimensionality of the problem from dimension n to a dimension beta in the previous example. But how can we understand the relation between the structure of the graph and these eigenvalues, and understand what are the situations when a graph will actually lead to the existence of this separation of eigenvalues and hence of timescales? And as we'll see, this will be something that will be related to the notion of modules. And to show so, well, let's consider an example, an extreme example. Let's assume that we consider a graph made of k modules. And actually, we're going to be having the adjacency matrix A. We'll be writing it as a part due to the structure plus a part due to noise. And we'll say that for the structure, we'll be assuming that each of the modules is a connected component. So we have k connected components, each of them characterized by their own adjacency matrix, plus a noise, plus some random connections that are added to the system. And actually the A noise can be modeled by an Erdős-Rényi graph, for instance. Now, starting from that adjacency matrix, you can define a Laplacian that's going to be equal to L structure plus L noise. Yeah. So let's first consider when L noise is equal to 0. Well, when L noise is equal to 0, we have k connected components. So the multiplicity of the eigenvalue 0 is k. Yeah. It basically means as well that we're going to be having a dominant eigenspace of dimensions k. And this subspace that we write A is going to be spanned by vectors Let me see. Well, by the corresponding eigenvectors. And actually, these eigenvectors are going to be of the following, organized as follows. So we can choose these eigenvectors to be, for instance, 1 inside a community and 0 here. For this one, 0, 1 inside that community and 0. And for this one, you're going to be having 0 and then 1. And each of these three are three eigenvectors where you have something that like constant vectors inside the three clusters. And if you combine them together, that defines this three-dimensional subspace associated to these three connected components. Now, clearly, now this is the case when the noise is equal to 0. Now, what's happening? And so, what is happening when L noise is small? Well, L noise is small. Well, clearly we can use results from metric perturbation theory, and in particular we can use the Davis-Kahan theorem, and it's going to show us that the subspace A prime that is spanned by the corresponding eigenvectors as the one of A is going to be actually very, very close to the one of A in situations when the noise is sufficiently small. And so it basically means that from this Davis-Kahan theorem, we will have that if we have a graph that is almost disconnected with three dense clusters and weak connections between them, we will have actually that the the subspace that is associated, that would be the dominant one, the one associated to the very small eigenvalues, those that are either 0 or very close to 0, which will actually be very close to the eigenspace that is spanned by these vectors that encode the communities, which basically means that indeed the communities, at least when the noise is small, is expected to control what would be what is the dominant eigenspace of your dynamical process. Now, just as an example to show how this works in practice. So here is an example where we have three graphs that are densely connected and weak connections between them, as in the previous example. And let's play the same game of letting the consensus dynamic have all starting from initial conditions that are random between -10 and 10. And if we let them run, and if we observe what's happening at a time of the order of 1 over lambda 4, yes? And this is the time when we can assume in principle that all of the modes associated to eigenvectors of an eigenvalue larger than lambda 4 will be going to 0. Well, actually what's happening is that indeed we have reached, as was predicted, local equilibrium, yes? And actually this local equilibrium is encoding is related to the communities that we have. We have that the red nodes are associated to the red local equilibrium, the blue nodes to the blue one, and the green one to the green. And we have, as you can see, a separation between the states of the green, the states of the blue, and the state of the reds, which basically means that indeed, well, in situations when we have time scale separation, we will have the possibility to have the emergence of local equilibria, and these local equilibria will be concentrated on nodes that belong to communities that are associated to the structure of the network. Thank you. So hello everyone, and welcome for this third video of the week, for week 5, where we will be talking about externally equitable partitions. So if you remember, in the first two videos, we've been interested in how groups of nodes are affecting dynamics. And we've seen that when a network exhibits a modular structure that will induce a separation of eigenvalues, and hence a separation in the time scales over which some dynamics takes place on graphs. Now, there are all sorts of other ways to find meaningful partitions where groups of nodes may have an impact on the dynamics. And a very important concept is the one of externally equitable partitions. So what are externally equitable partitions? I'm going to be giving you a definition and an example just after, but you need to think of it as some sort of a dynamics-based notion of equivalence between nodes. So we try to find groups of nodes that are equivalent from a dynamical perspective. Now, this notion of equivalence is actually very much related and can be seen as some sort of a generalization of standard concept in graph theory. And these concepts would be, for instance, the notion of structural equivalence. This was proposed by Laurent and White in the 1970s. So what is this notion of structural equivalence? You say that two nodes are equivalent if they have exactly the same neighbors. So that would be an example here. Let's say that they have a graph like this. And we have this kind of configuration. Well, these two nodes here would actually be said to be structurally equivalent because they have exactly the same two neighbors. Yes? And because of that, they will basically structurally equivalent at the level of the graph. Now, the notion of externally equitable partitions generalizes on this, but tries to find a notion of equivalence in relation to the role that the nodes play in linear dynamics. And typically they try to find not only pairs of nodes, but groups of nodes, and to try to partition the graph into groups of nodes that will be equivalent dynamically. So how do you define this notion of externally equitable partition? So typically, when you have an EEP, what you're going to be doing is to partition. There is a partition of the network into certain cells. Usually they're called cells instead of modules, because as you'll see, these cells don't really behave as according to the intuitive notion that you have about modules. And these cells, we write them Cj. And so it means that each node belongs to a certain cell Cj. Sorry, this C was a bit, Cj. Now, why would we call this partition externally equitable partition? So this partition is externally equitable if we have that for any node V in a certain cell Ci, it is connected to a fixed number of nodes in Cj. And this needs to be true for any ij. So it means that for any pair of cells, we need to have that when you have a certain node in one cell, it will be connected to a fixed number of nodes in another cell, which, as you see, reminds us with the notion of structural equivalence. So here would be an example of such an externally equitable partition, where what we would have here is that, for instance, if you consider all of those nodes here, well, each of them is connected exactly to one blue node, and each of them is connected exactly to 1, 2, 3 pink nodes, right? Similarly, if you consider, for instance, the blue nodes, each of them are connected exactly to one blue node, and, for instance, they're connected to 0 orange nodes. And you see that when you are part of a group, well, basically it means that the connectivity that you have to other group is a fixed number. So clearly these cells don't look like communities. For instance, you see that inside this orange, you have almost no connections. And indeed, actually in the definition of externally equitable partition, we don't say anything about the internal connectivity. We are just interested in some regularity in the connection between nodes that belong to different cells. And as we'll see, if we can find such an externally equitable partition, it will allow us to simplify quite drastically some analysis of a linear dynamical system taking place on networks. Now, when you have such and this cell, let's do it like this. So if you have such a externally equitable partition, actually you can encode it, and we're going to be encoding it. And sorry, this do it like this. We will be encoding them by a certain matrix n times k, where k is the number of cells, and this matrix is a matrix C that will be defined such that Cij is equal to 1 if node I belongs to the cell Cj. I will have that Cij is equal to 0 otherwise. So it means here that we are just encoding the partition. Yes? And we encode it by a rectangular matrix, n times k. N is the number of nodes, k is the number of cells. Now, when you think about that matrix C, well, you can see it as basically a sequence of vectors. You have C1, Ck, and each of them is a column vector, where C is a vector, and this vector indicates what are the nodes that are basically present inside the cell number I. Yeah? Very good. So now, once you have such a notation for the partition of the graph, well, actually it can be shown that a partition is EEP. It's EEP. Do I have this? Yes. A partition is EEP if we have that, if we take the Laplacian of the graph, the Laplacian that we've seen before, times this matrix C, it's going to be equal to C times the Laplacian that we call L pi. What is L pi? Actually, L pi is a k times k Laplacian, so where k is the number of cells, right, of an object called the quotient graph. So it means that we'll be constructing a quotient graph that's going to be a simplified version of the graph that is going to be smaller, and when we do so, we'll have that for a partition to be externally equitable partition, we'll need to verify this condition here. Now, how do we construct this L pi? Well, basically the L pi is going to be given by this expression here. So we have first C transpose C minus 1 C transpose, and then we have the L and the C, where actually this thing here can be seen to be a certain C plus. And what is the C plus? The C plus is a K times N matrix, and it is actually the Moore Penrose pseudo-inverse of the matrix C. And it can be the real inverse, because this is not a square matrix, but this is the pseudo-inverse of the matrix C. Now, there are a certain number of things that are important to note. So let's assume that I have a certain vector x that belongs to Rn, yes? And we multiply this vector by C transpose. If I do C transpose times the vector x, actually what it's going to be doing, it's basically, it sums the components within each cell. Actually, now if I consider the matrix C transpose C, what does it do? It's going to be a K times K matrix that gives you on the diagonal. So on the diagonal, it gives the number of nodes in each cell. Well, from those things, what we observe is that this C plus here that we've been defining can be understood as a cell averaging operator, in the sense that when you apply it, it's going to give you the average value of a certain value, vector x, where you only take the values of x inside the nodes that belong to a certain cell. So very good. Now, what is this quotient graph that we've been constructing? Actually, the quotient graph can be seen to be this object here, right? It's a graph that has a certain number of nodes, each node belonging that can be associated to a cell. And if we start from an undirected graph, in general, it's going to give us a directed quotient graph. And this quotient graph is such that each of the nodes are the cells, right? And we have weights that are defined on each of the directed edges that tell us the number of links that leave a node from a cell towards a node of another cell. So, for instance, from the orange, we know that from here we have one link that goes to the blue ones, and so that's why we have that in that direction we have a 1. While from the blue we have 4 links that go to the orange ones, and that's why we have a 4 here. And this actually encodes this structure and the number of connections that are fixed numbers, as we know, and that go from nodes from one cell to nodes of another cell. Very good. Now, the thing is that once we've been defining this quotient graph, it can be shown after some manipulation that C plus L is equal to L by C plus. Now, the thing is that this EEP actually can be understood as some sort of invariant of the Laplacian L. And as we'll see, this will lead actually to some interesting properties for the dynamics that would take place on the graph. So, what can we say? So, what would be the impact of these partitions on our understanding of some dynamics that takes place on the graph? Well, first of all, let's assume the following. So let's assume that we initially have that the states x that are defined on the nodes are equal to a certain c times y, where c times y basically means that we have y that is a vector of length c, so we have certain values that are assigned to each of the cells, and that basically means here that we give the value that is inside each cell to all the nodes inside that cell. Yeah? So, for instance, if here, as I would say that all of the nodes that would be orange would have the same value that would be corresponding to the value that is defined for that cell. And that would be, for instance, that all of them has a value of 0.5. All of those would have a value of 0.1, for instance. This one 0.0, and so on. So you assign constant values to all of the nodes inside the cells. Well, actually, what can be shown is that this relation will be satisfied for all time. So it means that if you start initially with all of the nodes that have the same value, a value that is defined at the cell level, well, this will be satisfied for all times, and all of the dynamics will actually take place at the level of the y's, and we'll have that y dot is going to be equal to minus L transpose L pi, so L minus the L pi times the vector y. So it means now that if you want to understand the dynamics of the nodes, you don't need to solve the dynamics of the n times n system. You can simply look at the dynamics of the k times k system. Yeah, it's going to lead to an evolution, and we will have that the time evolution of the states that are defined on inside the cells will always be the value that is for all of the nodes inside these cells. Yes? Which is a very strong symmetry that is present inside the dynamics. Now, this is something that can be observed. Another thing that is directly related is that, so now let's assume that we define the cell averaged states, average of x inside the cell Ci. So here we don't assume that x take a constant value inside the cell, but we consider the average of these values inside cells. Yeah? But then what can be shown again is that we can write that d of the average inside Ci dt is going to be equal to minus this L pi as before times the average of x Ci. Yes, the same equation as before. Yeah. So it means that we have a closed equation for the average value inside each of the cells. And how do we define this one? We have that this x inside the cell Ci, as we said before, is obtained from the C plus, this cell averaging operator, is equal to this C plus times the vector x. So it means here that we have two important properties. If the values are constant inside cell, it will be the same for all times, and we have a simplified dynamics. The other one is that if it's not constant, but we are only interested in the average value inside the cells, well, we can write again a smaller set of equations that can predict us the time evolution of these averages inside each cell. So let's see how this works in practice. So this is here the same example. We have the graph, we have the quotient graph. And here on the left, we've been giving the same value for all of the red nodes, all of the blue nodes, all of the orange nodes, and so on and so forth. And what you can see is that the dot lines are corresponding to the dynamics that is obtained by solving the n times n system, while these rounds are obtained from the simplified dynamics that is here. And clearly you see that there's a perfect match between the reduced dynamics and the complete dynamics. Now another example would be here. Now I've been considering a situation where I give random values to all of the nodes. And so for instance, you see that the orange ones have different values. So you have here some of them, another one here, and I guess that the last one would be somewhere, I don't know, somewhere here, I guess. And if you now consider the average across all of those, well, that would be again this line, and that would be the line that's obtained from taking an average of the solution obtained from the n times n equation. And what you observe is that again, this average behavior can be exactly solved by looking at this reduced set of equations that we have here. So it means that what we've been finding here is actually another type of partition that is quite important in order to understand dynamics. But what I would like to do here is to show the important difference that exists between the modules that we were interested in the last two videos and these externally observable partitions. So in the case of modules, what we were interested in was the concept of timescale separation. What we were interested in was the fact that you would have a certain timescale separation that would be such that after some time, we would reach a local equilibrium inside the communities, and that only afterwards these communities would converge to the global consensus. Yes. So it means that thanks to this separation of variables, we can be sure that after a certain amount of time, we'll have that the vectors will be mostly constants inside each of the communities. Here actually, for these externally equitable partitions, we have something that is very much different. And actually, we are not interested in the eigenvalues at all, but what we're interested in are more the eigenvectors of the Laplacian. And indeed, it can be shown that when you have an externally equitable partition, actually, there's going to be a set of eigenvectors that will be exactly constant on each cell of the graph. And the existence of these eigenvectors actually is related to the presence of symmetries that are present in the graph structure, and the symmetry that then help us to simplify the dynamics. Now, indeed, something that's quite important to understand is that when we have this notion of externally equitable partition, well, what we look for are cells of nodes that basically behave similarly. But something that's quite important to understand as well is that even if these nodes, for instance, the dynamics of these nodes can be written in a simplified way, we cannot be sure at all, because we don't rely on a separation of timescales, that these nodes will reach a local consensus before reaching the global consensus. So it means that here, for the externally equitable partitions, what we can say, we can derive exact equations for the average behavior inside the cells. And so by then lowering the dimensionality of the problem. While in contrast, when we looked for modularity, we couldn't write exact equations for the average behavior inside the cells, but we could be sure that after some time, we would have that most of the nodes would have come very close to that local average, and that would then have led to a reduced dynamics. And so it means here that we have two very different principles, two very different mechanisms that basically lead to a reduction of the dimensionality of the problem, each one defining a different type of partition. One that is really about modularity, dense groups of nodes. The other one, associated to the externally executable partition, that is more about the existence of regularities in the connectivity existing between different groups of nodes. Okay? So, well, that was what I wanted to tell you about these impacts of graphs and some structures, some hidden structures inside the graph on dynamics. And, well, actually, next week and the week after, we will continue our journey on the dynamics on networks. Thank you very much.